across the unfathomable darkness of the void, a silent narrative unfolds. It is a story not written in words, but in light and its absence. We are accustomed to a universe ablaze with creation, a cosmos teeming with stellar nurseries. Vast iridescent clouds of gas and dust collapse under their own gravity. They ignite into the brilliant fires of 1 trillion suns, painting the cosmic canvas. This is the universe of life, of vibrant spiral arms and bustling stellar metropolises. But there is another side to this story, a quieter, more somber chapter. Out in the profound depths, there exist other kinds of cosmic structures. Celestial cities where the lights have gone out, where the fires of creation have been extinguished. These are the galactic graveyards, ancient and immense island universes that no longer give birth. They drift through the intergalactic medium as ghostly relics of a more vibrant past. They are serene, yet unsettling, their populations of aging, red stars a silent testament to a forgotten age of glory. What great and terrible power could halt the most fundamental process in the cosmos? What force can sterilize a structure containing hundreds of billions of suns, rendering it barren for eternity? Tonight, we embark on a journey to these enigmatic realms. We will become cosmic detectives, seeking clues in the ancient light of the distant worlds. We will investigate the celestial assassins, the colossal forces and violent events that murder galaxies. This is a voyage to the edge of cosmic life and death, a quest to understand the deadly galaxies that kill the stars. To comprehend an ending, we must first appreciate the beginning. Our own home, the Milky Way, serves as our perfect specimen of a living, breathing stellar system. It is a sprawling spiral assembly, 100,000 light-years across, a celestial pinwheel of staggering beauty. Within its graceful arms, the grand cycle of cosmic life plays out in an eternal loop. Look closer, into the nebulae, those ethereal clouds that glow with the soft pastels of ionized hydrogen and oxygen. These are the wombs of the universe, the stellar nurseries where the magic begins. Think of them as vast reservoirs of primordial material, a delicate mist of hydrogen and helium left over from the Big Bang. For billions of years, this cosmic fuel has floated, diffuse and cold. But the universe is never truly still. The subtle influence of gravity is always at work. A passing shockwave from a distant supernova, or the gentle gravitational nudge of a neighbouring star can disturb this delicate equilibrium. A small region within the cloud begins to contract, an imperceptible gathering of matter. As it shrinks, its gravitational pull intensifies, attracting more and more material in a runaway process. This collapsing core, known as a protostar, begins to heat up, its centre glowing a dull, angry red. For millennia, this process continues, the core growing hotter and denser, until a critical threshold is reached, a point of no return in temperature and pressure, 10 million degrees Celsius. At this ferocious temperature, the very fabric of matter is transformed. Hydrogen atoms, the simplest building blocks of the universe, are forced together with such violence they fuse. They merge to become helium, and in that transformation, a tiny fraction of their mass is converted into a colossal burst of energy. A star is born. A new light shines in the cosmos, a self-sustaining fusion engine that will burn for billions of years. This process is not isolated. It is happening thousands of times over throughout our galactic home. The Milky Way is a vibrant ecosystem of creation. Imagine a colossal, self-sustaining rainforest, impossibly ancient and vast. The interstellar gas is the fertile soil from which everything grows. The brilliant young blue stars are the fresh saplings, burning through their fuel with reckless abandon. Sun-like stars, such as our own, are the mature, steady trees in the heart of the forest, providing stability. And the massive red giants are the ancient sequoias, nearing the end of their majestic lives. When these giants finally exhaust their fuel, they do not simply fade away. They erupt in a supernova, the most spectacular death imaginable in the cosmos. In this final cataclysmic explosion, they scatter their ashes across the interstellar medium. But these are no ordinary ashes. They are enriched with the heavy elements forged in the star's nuclear heart: carbon, oxygen, iron. the very elements necessary for planets, for life, for us. This enriched material seeds the surrounding clouds, enriching the cosmic soil. It provides the raw ingredients for the next generation of stars and planetary systems. This is the galactic circle of life, a continuous self-regulating process of birth, death, and rebirth. The engine of this entire cycle, the one non-negotiable ingredient, is the galaxy's vast reservoir of cold molecular gas. Without this fuel, the forest cannot grow. Without this primordial material, no new saplings can take root. The fires of creation would cease, and the entire ecosystem would slowly, inexorably begin to die. This is the vital context we need. This is the baseline of a healthy, thriving island universe. Now, armed with this understanding, our journey can truly begin. We leave the familiar luminous arms of the Milky Way behind. Our destination lies in the desolate voids between galactic clusters and in the turbulent hearts of the largest cosmic structures. We are hunting for the culprits responsible for galactic homicide. Our first suspect is perhaps the most intuitive, a killer acting on a scale almost too large to contemplate. It is the act of galactic cannibalism. Galaxies are not solitary islands, eternally separated by the void. They are social creatures, bound by the invisible threads of gravity into groups and massive clusters. And in these crowded cosmic neighborhoods, interactions are not just common, they are inevitable. What begins as a delicate gravitational dance between two approaching stellar systems can escalate into a violent, transformative collision. Imagine two immense whirlpools of light, each containing billions of suns, on a collision course over millions of years. As they draw closer, their outer arms begin to feel the other's pull. Gravity reaches across the darkness, distorting their elegant spiral shapes. Long, luminous tendrils of stars and gas, known as tidal tails, are drawn out into the void. They stretch for hundreds of thousands of light years, a ghostly testament to the titanic forces at play. Then, the two structures begin to merge. Contrary to what one might expect, individual stars rarely, if ever, collide. The distances between them are simply too vast. Instead, they pass through each other like phantom fleets of ships in the night. But the gas clouds, the vast, diffuse stellar nurseries, are another matter entirely. They are not small, dense points of light. They are enormous, sprawling structures. When these clouds from opposing galaxies slam into each other, they collide with unimaginable force. The impact creates massive shockwaves that ripple through the combined interstellar medium. These shockwaves compress the gas to incredible densities, triggering a frenzy of star formation. This is an event known as a starburst. It is not the gentle, steady creation of stars we see in the Milky Way. This is a cosmic conflagration. An entire galaxy's worth of gas is consumed in a fury of creation that is hundreds, even thousands of times more intense than normal. The newly merged system shines with a brilliant blue-white intensity, a beacon of ferocious activity. But this magnificent display is a prelude to death. It is a bonfire that burns 1,000 times as bright, but for a fraction of the time. In a stunningly short period, cosmically speaking, perhaps only a few 100 million years, the starburst consumes virtually all of the available cold gas. The fuel for future generations of stars is gone, used up in one last, glorious blaze of glory. What remains after the firestorm subsides is a new, much larger entity. The chaotic merger scrambles the orderly, rotating disks of the original spiral galaxies. The resulting structure is a bloated, disordered sphere or ellipsoid of stars. This is the birth of a giant elliptical galaxy. Its stellar population is now dominated by the longer-lived, smaller, redder stars. There is no gas left to form new, brilliant blue ones. The stellar nurseries have all been paved over. The celestial city, once a vibrant hub of creation, has become a sprawling, silent retirement community for aging suns. This cannibalistic act, this merger-driven starburst, is a highly effective method of quenching a galaxy. It drains the lifeblood of a system in a final, spectacular burst, leaving behind a beautiful but sterile ghost. These crimson behemoths are often found reigning at the centres of massive galaxy clusters. They are the cosmic kings who grew to their immense size by devouring their neighbours and now they sit dormant on their thrones. But galactic murder is not always so straightforward. Sometimes the killer is not an external invader, but a monster lurking within the galaxy's own heart. For decades, astronomers were puzzled by fantastically bright star-like objects in the distant universe. They were called quasi-stellar radio sources, or quasars. Their light was so powerful they outshone their entire host galaxies by a factor of 1,000. What engine could possibly generate such an astronomical amount of energy from such a compact region of space? The answer was more terrifying and more awesome than anyone had imagined. At the centre of almost every large galaxy, including our own Milky Way, resides a supermassive black hole. These are not the stellar mass black holes left over from dying stars. These are primordial monsters, millions or even billions of times the mass of our Sun. Most of the time they are dormant, sleeping giants in the galactic core. But if a large amount of material, a stray star, a massive gas cloud, wanders too close, the beast awakens. As matter is pulled toward the event horizon, it doesn't fall straight in. It forms a swirling chaotic vortex around the black hole called an accretion disk. Friction and magnetic forces within this disk heat the material to millions of degrees. It glows with an impossible brilliance, radiating more energy than all the stars in the galaxy combined. This is the engine of a quasar. The galaxy's central black hole is feeding. This process, known as an active galactic nucleus, or AGN, is one of the most violent phenomena in the universe, and it has profound consequences for its host. The intense radiation pouring from the accretion disk acts like a cosmic blowtorch. It blasts through the galaxy, heating the cold, dense gas clouds required for star formation. It ionizes them, stripping their electrons away and raising their temperature by millions of degrees. This hot gas is now too energetic, too diffuse to ever collapse and form new stars. The process is a form of galactic sterilization, rendering the stellar nurseries inert. But it gets even more violent. The supermassive black hole doesn't just radiate energy, it can also expel matter. Twisted magnetic fields, generated by the spinning black hole and the accretion disk, can act like cosmic particle accelerators. They can capture some of the infalling material and launch it outwards in two colossal jets of plasma. These jets travel at speeds approaching the velocity of light itself. They are fired from the poles of the black hole, perpendicular to the accretion disk. They are so powerful they can punch clear through the entire galaxy and travel for millions of light years into intergalactic space. As these jets tear through the host system, they act like a cosmic snowplow. They sweep up and blast away enormous quantities of the interstellar medium. The precious, life-giving reservoirs of cold gas are violently ejected from the galaxy altogether. This mechanism is known as AGN feedback. It is the galaxy's own central engine turning against it, a form of cosmic autoimmune disease. Imagine a beautiful, fertile garden ready for planting. Now imagine a gigantic industrial pressure washer at the garden's centre, running uncontrollably. It blasts away the topsoil, shreds the seeds, and scours the landscape down to the bedrock. Nothing can ever grow there again. This is what a powerful quasar can do to its own stellar metropolis. It's a process of self-annihilation, driven by the monster at its core. Many of the quiescent red and dead galaxies we observe show evidence of this violent past. They possess the gargantuan black holes necessary for such an event. Their galactic halos are filled with superheated gas, a faint X-ray glow that speaks of a time when their centres burned with unimaginable fury. The central beast, having consumed all the nearby fuel and driven the rest away, eventually starves and falls dormant again. But the damage is done. The city has been sterilized, the celestial rainforest has been turned into a desert, and the galaxy is left to drift through eternity, a silent monument to its own self-destructive power. Yet another form of galactic death is more subtle, a slower and more insidious demise. It is a death by 1,000 cuts, an environmental hazard of living in the wrong neighborhood. The universe is not uniformly distributed. Gravity has woven matter into a vast, intricate structure called the cosmic web. This web is composed of long, tenuous filaments of gas and dark matter, connecting massive nodes. These nodes are the galaxy clusters, the great megacities of the cosmos. Here, thousands of galaxies are packed together in a relatively small volume of space, all orbiting a common centre of gravity. But these clusters are not empty. The space between the galaxies is filled with something called the intra-cluster medium. It is diffuse, incredibly hot plasma, heated to tens of millions of degrees, visible only to X-ray telescopes. This superheated gas is the remnant of primordial material and matter stripped from galaxies over eons. For a small gas-rich spiral galaxy, falling into one of these clusters is a death sentence. As the unsuspecting galaxy plunges into the cluster at millions of kilometers per hour, it encounters this hot, dense medium. The effect is like a person running headfirst into a hurricane. The intracluster medium exerts an immense pressure on the galaxy, a force known as ram pressure. This cosmic wind is so powerful, it can literally strip the cold star-forming gas right out of the galaxy's disk. We have observed this process in action. Telescopes like Hubble have captured stunning images of so-called jellyfish galaxies. These are spirals falling into clusters, with spectacular trailing tentacles of blue, star-forming gas being ripped away from them. It is a beautiful yet tragic sight. We are witnessing a galaxy being murdered in real time. Its lifeblood is being drained away, leaving a spectacular trail of new stars that will be orphaned in intergalactic space. Once the galaxy has been fully stripped of its fuel, its ability to form new stars is extinguished forever. It will continue its orbit within the cluster, but it is now just a husk, a collection of old stars fated to slowly fade. This ram pressure stripping is a brutally effective killing mechanism in the densest regions of the universe. But there is an even slower, more passive environmental process at play. It is a form of cosmic strangulation. Galaxies like our Milky Way are not closed systems. They are constantly accreting fresh, cool gas from the cosmic web, trickling in along those great filaments. This is the supply line that replenishes the stellar nurseries and sustains star formation over billions of years. When a galaxy is pulled into the gravitational well of a massive cluster, that supply line is severed. It becomes disconnected from the life-giving filaments of the cosmic web. The galaxy can no longer draw in fresh fuel from the outside universe. This process is called starvation. The galaxy is not violently stripped of its existing gas. Instead, it is simply cut off from its food source. It can continue to form stars for a time, using up its remaining internal reserves. But this is a finite supply. Like a city under siege, its resources slowly dwindle. Star formation rates gradually decline over billions of years. The vibrant blue of young stars slowly gives way to the telltale red of an aging population. The spiral arms fade, the nebulae dissipate, and eventually the last stellar nursery goes dark. The galaxy has been slowly, quietly strangled to death. It has become another quiescent member of the cluster, its fate sealed by its cosmic address. These three assassins, violent mergers, self-destructive black holes, and hostile environments are the primary culprits in our investigation. Each uses a different method, but the outcome is always the same: the cessation of star birth, the slow fading of light, and the creation of a silent, dead galaxy. The evidence for these cosmic crimes is not found in a laboratory on Earth. It is gathered by humanity's greatest scientific instruments, our silent eyes on the cosmos. Telescopes are time machines. Because light takes time to travel across the vastness of space, when we look at a distant galaxy, we are seeing it as it was in the past. By looking at galaxies at different distances, we can piece together a cosmic history. We can see the universe when it was younger, more turbulent, and filled with brilliant blue, actively forming stellar systems. And we can see how, over time, more and more of these have transformed into the red, quiescent behemoths we find in the modern universe. The Hubble Space Telescope has been our primary detective for decades. Its sharp vision allows us to resolve the shapes and colours of galaxies billions of light-years away. It was Hubble that showed us the distorted, mangled forms of colliding galaxies. It captured the beautiful, tragic trails of jellyfish galaxies being stripped of their essence. And it helped us classify the two great populations of galaxies: the blue cloud of active star formers and the red sequence of passive dead systems. To understand the invisible forces at play, we need to see the universe in different kinds of light. The Chandra X-ray Observatory is crucial. It maps the superheated million-degree gas in the intracluster medium, the very substance responsible for ram pressure stripping. Chandra can also see the X-ray glow from the accretion disks around supermassive black holes, and it can trace the immense bubbles and cavities carved out in galactic halos by the jets from powerful AGN feedback. Radio telescopes, like the Very Large Array, perform a different kind of autopsy. They are tuned to detect the faint radio waves emitted by cold hydrogen gas, the raw fuel for star formation. By pointing these instruments at a red elliptical galaxy, astronomers can confirm our suspicions. They find that there is, indeed, a profound lack of this crucial ingredient. The gas tank is truly empty. But perhaps the most powerful tool in our arsenal is the computer simulation. Cosmologists can create virtual universes inside supercomputers. They can input the laws of physics, gravity, gas dynamics, the life cycle of stars, and watch how galaxies form and evolve over billions of years. These simulations allow us to test our theories. We can model a galactic merger and see if it produces a red elliptical. We can simulate a galaxy falling into a cluster to watch ram pressure stripping in action. We can turn on AGN feedback and observe how it quenches star formation. When the results of these simulations closely match what we actually observe in the sky with our telescopes, we gain confidence that we are on the right track. We are beginning to truly understand the complex web of forces that governs the life and death of a galaxy. The evidence is overwhelming. The universe is not just a stage for creation, it is also an arena of destruction and transformation. The silent red galaxies are not anomalies. They are the natural, inevitable endpoint for many cosmic systems, the result of a violent and chaotic past. This cosmic drama is not just an abstract story playing out in the distant universe. It is a preview of our own future. Our Milky Way galaxy is not alone. We are on a collision course with our nearest large neighbour, the Andromeda Galaxy. Right now, Andromeda is 2.5 million light-years away, but it is hurtling towards us at a speed of over 400,000 kilometers per hour. In about 4.5 billion years, the two great spirals will collide and merge. Our distant descendants, should they exist, will be treated to the most spectacular light show in celestial history. The sky will be filled with the distorted arms of Andromeda, a canvas of brilliant nebulae and furious star formation. The collision will likely trigger a massive starburst, consuming much of the combined gas reserves of both galaxies. The supermassive black holes at the centres of both galaxies will also merge. This event will create a new, even larger black hole, and could trigger a powerful quasar phase, further purging the system of any remaining gas. The result of this cosmic crucible will be a new giant elliptical galaxy. Astronomers have already nicknamed it Milkomeda. Our familiar elegant spiral home will be gone, replaced by a vast disordered sphere of aging stars. The era of star formation in our local corner of the universe will be over. Our galaxy will have joined the ranks of the red and the dead. This is not speculation, it is a gravitational certainty. And this story of quenching and decay may be the ultimate fate of the entire universe. The cosmos is expanding, and that expansion is accelerating. Galaxies are flying further and further apart. The great clusters will remain gravitationally bound, but they will become ever more isolated islands in an ever larger void. Within these clusters, the processes of murder will continue. Mergers, stripping, and starvation will slowly convert the remaining blue spirals into red ellipticals. The supply of fresh gas from the cosmic web, already thinning due to expansion, will cease entirely. The universe will slowly run out of the fuel needed to create new stars. The era of stellar formation, the stelliferous era in which we are so lucky to live, will come to an end. The last stars will be born. The universe will then be populated only by long-lived, dim red dwarf stars and the cooling embers of stellar remnants, white dwarfs, neutron stars, and black holes. For trillions upon trillions of years, the cosmos will grow darker and colder. The last red dwarf will finally flicker and die. The universe will become a silent, empty place of unimaginable cold and darkness. A sea of degenerate matter and black holes slowly evaporating through Hawking radiation over timescales that defy human comprehension. The deadly galaxies we see today are not aberrations. They are pioneers. They are messengers from the far, far future, a glimpse into the ultimate fate of all matter and all light. Their profound silence speaks of the inexorable march of entropy, the universal tendency towards disorder and decay. The journey to these cosmic graveyards is therefore a journey to the end of time itself. It forces us to confront the mortality of not just ourselves, but of everything we see and know, of the stars, the galaxies, and the cosmos as a whole. But there is a strange beauty in this conclusion. It places our own existence in a context of breathtaking significance. We live in the universe's vibrant, youthful morning, a fleeting, glorious moment when the cosmos is alive with the fire of creation, a time when the night sky is not yet dark, a time when new suns are still being forged in clouds of incandescent gas. The silence of the dead galaxies reminds us that this cosmic spring will not last forever, and it implores us to cherish the light, the life, and the brilliance of the universe we call home. For we are the children of the stars, born in a living galaxy, and privileged witnesses to the grand and ultimately finite cosmic dawn. What if the universe's greatest act of creation is born from its ultimate engine of destruction? You are looking at a paradox written in fire across the cosmos, a celestial contradiction that stretches for millions of light years. At the heart of a distant galaxy, an object of unimaginable density, a supermassive black hole reigns in absolute darkness. Its gravitational pull is so profound, so inescapable, that not even light, the fastest thing in existence, can break free. It is the end of the line, a one-way journey into oblivion for any star planet or cloud of gas that strays too close. By all accounts, this should be a place of finality, a cosmic tomb from which nothing returns. And yet from the very edge of this abyss erupts a spectacle of such ferocious power it can alter the fate of the entire galaxy around it. These are the great jets, twin beams of matter and energy accelerated to within a whisper of the speed of light. They are not just phenomena, they are the universe's most violent artists sculpting the heavens with a celestial blowtorch. For decades we believed we understood their fundamental nature, their unwavering constancy. We saw them as pillars of stability in a chaotic cosmos, their direction fixed, their purpose clear. We were wrong. We were profoundly, spectacularly wrong. A discovery has been made that rips up the textbooks, forcing us to confront a universe far more volatile and unpredictable than we ever dared to imagine. A universe where even these cosmic titans, these anchors of galactic structure, can suddenly and violently change their minds. To truly grasp the scale of this revelation, you must first journey with us into the maelstrom at a galaxy's core. Picture a gravitational well of impossible depth, a distortion in the very fabric of space-time created by a mass, millions or even billions of times greater than our own sun. This is the domain of the supermassive black hole. It does not shine. It is a void, a perfect sphere of blackness defined only by the chaos that surrounds it. This chaos has a name, the accretion disk. It is the final, desperate dance of matter spiraling towards its doom. Entire solar systems ripped apart by tidal forces are stretched into incandescent ribbons of gas and dust. This material, unable to fall in directly, forms a vast, flattened whirlpool, a cosmic drain of unimaginable proportions. The friction here is so intense, the collision so violent, that the disk glows with a ferocity that can outshine all the billions of stars in its host galaxy combined. It is a terrifying, beautiful spectacle, a blaze of glory at the threshold of oblivion. Temperatures soar to millions of degrees, unleashing a torrent of X-rays and other high-energy radiation. This is the black hole's last luminous warning sign. The inner edge of this disk moves at a staggering fraction of the speed of light, a relentless gravitational conveyor belt feeding the insatiable monster at its center. This is the point of no return, the event horizon, the boundary from which no information can ever escape. Here our understanding of physics breaks down and the familiar universe ceases to exist. For years, a fundamental question puzzled astronomers: how can a creature of pure consumption, an entity that only takes produce the most powerful outflows we have ever witnessed? The answer, we believe, lies not in what falls in, but in the terrifying physics of the fall itself. The supermassive black hole is not just a static gravitational pit, it is a dynamic spinning engine. It spins with a colossal angular momentum dragging the very fabric of space-time around with it in a cosmic vortex known as frame dragging. As the superheated plasma of the accretion disk spirals inwards, it carries with it intense magnetic fields. These fields, born in the hearts of the stars that were consumed, become entangled in the black hole's dizzying spin. They are twisted, stretched, and coiled into titanic helical structures, like cosmic springs being wound to an impossible tension. This process transforms the rotational energy of the black hole itself into a different kind of power. The spinning, magnetized space-time acts like a colossal dynamo, an electrical generator of galactic proportions. It creates an environment so extreme that it can overcome the black hole's own gravity. From the poles of this spinning beast, where the magnetic field lines are most tightly wound, a path of escape is forged. An escape for some of the doomed matter. Particles caught in this magnetic crucible are seized from the innermost edge of the accretion disk, just moments before their final plunge. They are then funneled and accelerated along these magnetic field lines away from the black hole, away from the galaxy's core. This is not a gentle process. It is an eruption of cataclysmic force. The particles are propelled outwards in two perfectly opposing, tightly collimated beams, pencil-thin on a cosmic scale, but carrying the energy of trillions of stars. This is the birth of a jet. It is the black hole's defiant roar, a testament to the fact that even at the edge of forever, the laws of conservation of energy demand a reckoning. Nothing is truly lost. It is merely transformed into something else, something terrifyingly powerful. Once launched, these jets embark on a journey of cosmic engineering, becoming far more than just a spectacular light show. They are fundamental architects of galactic evolution, a crucial component in the grand feedback loop that governs how galaxies live and die. As jet plows through the interstellar medium of its host galaxy, it acts like a snowplow of unimaginable force. It carves out vast empty cavities in the gas and dust, some stretching for hundreds of thousands of light-years, far larger than the visible galaxy itself. These are the radiolobe's immense bubbles of high-energy particles and magnetic fields visible only to our radio telescopes. They are the ghostly remnants of the jet's passage, the scars left upon the galactic landscape. This process has profound consequences. By clearing out these vast regions of gas, the jet effectively removes the raw material for star formation. It can shut down a galaxy's stellar nurseries, preventing it from forming new stars and forcing it into a premature, quiet old age. A galaxy's supermassive black hole in this sense regulates its own growth. If it feeds too quickly, it launches powerful jets that clear out its food supply, a self-limiting cycle that plays out over billions of years. But the jet's influence is not purely destructive. In other circumstances, the immense shock waves generated by its passage can compress clouds of gas, triggering frantic bursts of starbirth, where none might have occurred otherwise. The jet is both a creator and a destroyer, a giver of life and a sterilizing agent. It also serves as a galactic enrichment program. The material fired out in these beams is not just hydrogen and helium from the early universe. It contains heavier elements forged in the hearts of stars that were later consumed by the black hole. These jets become colossal distribution systems, seeding the intergalactic medium with the carbon, oxygen, and iron necessary for the formation of new solar systems, new planets, and perhaps new life. Without them, galaxies might be wildly different places, chaotic, bloated balls of stars, or perhaps anemic and underdeveloped. The jets provide a structure, a discipline, a galactic backbone that dictates the very shape, size, and destiny of the stellar city they inhabit. Understanding their role as galactic architects meant that for decades we built our models on one seemingly unshakable foundation, the principle of stability. We came to see the jet's direction as something almost immutable, a fixed pointer in the cosmic chaos. This idea was rooted in a concept of profound elegance. The jet, we reasoned, is powered by the black hole's spin. Therefore, its axis must be perfectly aligned with the spin axis of the black hole itself. A supermassive black hole is the ultimate gravitational gyroscope. Its immense mass and angular momentum give it a staggering rotational inertia, a resistance to any change in its orientation. Think of a spinning top. The faster it spins, the more stable it becomes, stubbornly resisting any attempt to knock it over. Now amplify that principle to an object containing the mass of 4 billion suns. The forces required to alter its spin axis are almost beyond comprehension. Merging with another supermassive black hole might do it, but such an event is a cataclysm of rare violence, and the system would be expected to settle down over millions of years. For all intents and purposes, we treated the spin axis as a fixed constant property of the galaxy. This assumption was axiomatic. It was the bedrock upon which we built our understanding of active galactic nuclei. We observed countless galaxies with jets punching straight and true, their radio lobes forming beautiful symmetrical patterns on either side. We saw no evidence to the contrary. These celestial lighthouses, we concluded, did not waver. Their beams were locked in place for eons, dutifully carving the same channels through their galaxies century after century, millennium after millennium. This stability was comforting. It introduced a degree of order of predictability into our models. It allowed us to trace the history of a galaxy's activity by looking at the alignment of its ancient radio lobes, assuming they all pointed back to the same unwavering central engine. It was a simple, powerful, and universally accepted truth. It became the central dogma of jet physics, a fact so self-evident that to question it seemed almost absurd. But the universe rarely cares for our assumptions, and it has a habit of hiding its greatest secrets in the subtle deviations from the patterns we expect. For years there were whispers in the data, strange footnotes in astronomical papers that hinted at something amiss. Astronomers would occasionally find galaxies with X-shaped radio lobes, where fainter older lobes were oriented at a completely different angle to the bright active ones. The prevailing theory was that these were the products of a rare galactic merger, where two supermassive black holes had combined, violently reorienting the spin of the final merged object. It was a plausible explanation, but it relegated these strange systems to the category of cosmic oddities, the exceptions that proved the rule of stability. In other cases, we saw jets that appeared bent or distorted. We attributed this to the jet interacting with dense clouds of gas in the host galaxy, like a stream of water being deflected by a rock. We called this jet-cloud interaction, another neat explanation that kept the core principle of a stable central engine intact. We were creating ever more elaborate justifications to protect a cherished idea. We found what we expected to find, and we explained away the data that didn't fit. The anomalies were there hiding in plain sight, but the paradigm was so strong, the belief in the gravitational gyroscope so deeply ingrained that we couldn't see the forest for the trees. We were looking at the evidence of a revolution without recognizing it for what it was. These were not mere peculiarities. They were clues. They were the first tremors heralding a seismic shift in our understanding, a crack forming in the very foundation of astrophysics. The universe was trying to tell us something. It was trying to tell us that the gyroscope could wobble, that the pillars of creation were not fixed, that the heart of the galaxy was not a steady constant engine, but something far more dynamic and far more terrifying. The stage was set for a discovery that would transform these scattered anomalies from curious footnotes into the opening chapter of a new story. All that was needed was the right instrument looking at the right galaxy at the right time with enough precision to catch the engine in the act of changing its mind. We had built a picture of a predictable cosmos governed by forces that, while immense, operated on timescales of millions or billions of years. We accepted that a jet's direction could change, but only as the result of a cataclysmic merger or once-in-an-eon event. The idea that it could happen spontaneously rapidly without any obvious external cause was simply not on the table. It was scientific heresy. What would it mean if these cosmic blowtorches could suddenly swing around like a loose fire hose and point in a new direction? The implications were staggering. Entire regions of a galaxy previously untouched could suddenly be blasted by a torrent of high-energy particles. Star-forming regions could be snuffed out in an instant. The entire regulatory system of the galaxy would be thrown into chaos. It would mean our assumption of order was an illusion. It would mean that the hearts of galaxies are not stable, but fickle. This forces us to ask a question that cuts to the very core of our understanding of these cosmic powerhouses. What if the axis of the jet is not inextricably linked to the spin of the black hole? What if some other, more volatile mechanism is at play, a mechanism that allows the universe's most powerful weapons to re-aim themselves on timescales we had previously considered impossible? An observation has been made that provides a shocking, unambiguous answer. We have for the first time seen it happen, and it has sent shockwaves through the astronomical community, forcing us to re-evaluate everything we thought we knew about the relationship between a black hole and the galaxy it commands. What if the most destructive force in the known universe, a force that rips stars apart and devours light itself, is also one of its greatest architects? This is not a riddle, but the profound paradox that lies at the heart of every great galaxy, including our own. For decades we have looked to these cosmic behemoths, these supermassive black holes, and seen them as the silent tyrants of their stellar empires, gravitational anchors around which trillions of suns dutifully orbit. We have measured their shadows, calculated their masses, and marvelled at their sheer uncompromising power to end all things that stray too close. Yet this portrait of a purely passive, gluttonous monster is tragically incomplete. It misses the truth of their violent creative and galaxy-shaping fury. It misses the story of their phenomenal cosmic jets. To understand these magnificent structures, you must first journey with us to the most extreme environment imaginable, the galactic core. Here at the very centre, the gravitational heart of a galaxy beats with an inexorable rhythm. This is the domain of the supermassive black hole, an object of such density that it has collapsed space-time into a singularity, an object whose mass can equal that of billions of our suns, all compressed into a volume smaller than our solar system. It is a silent predator waiting. But its hunting ground is not empty. The galaxy is a swirling metropolis of gas dust and countless stars, and not all of it can maintain a safe, stable orbit. Over cosmic timescales, through galactic mergers, or the slow decay of orbits, vast clouds of interstellar material begin a final, inexorable pilgrimage toward this central point of no return. This material does not simply fall in. As it is drawn closer by the black hole's prodigious gravity, it brings with it a memory of its own motion, its angular momentum. This cosmic inheritance prevents a direct plunge, forcing the infalling matter into a spiraling dance of death. This is the birth of an accretion disk, one of the most luminous and violent objects in the entire universe. Imagine a spinning platter of matter, stretching for billions of kilometers, a cosmic maelstrom where entire solar systems would be ground to their constituent atoms. The inner edge of this disk whips around the black hole at a staggering fraction of the speed of light, while the outer regions move more slowly. This difference in velocity creates unimaginable friction, a celestial grinding wheel that heats the gas and dust to temperatures of millions, even billions of degrees. The light you are seeing from this process, the brilliance of a quasar that can outshine its entire host galaxy, is not coming from the black hole itself. The black hole by definition is perfectly dark. Instead, you are witnessing the death scream of matter, the incandescent fury of its final moments before it crosses the event horizon. This disk is the inferno of superheated plasma glowing with such intensity that it radiates across the entire electromagnetic spectrum from low-energy radio waves to the most energetic searing gamma rays. It is a place where the fabric of reality is stretched thin, where matter is converted into pure energy with an efficiency that dwarfs any nuclear reaction we could ever hope to create. Every particle, every atom is on a one-way trip, compressed, superheated, and shredded on its journey toward the ultimate abyss. We thought this was the end of the story, a cosmic drain where the universe's substance vanishes forever. But from this vortex of annihilation, something impossible happens. From the very edge of oblivion, life, in a manner of speaking, springs forth. Two colossal, tightly focused beams of matter and energy erupt from the poles of the black hole perpendicular to the swirling plane of the accretion disk. They are the black hole jets, and they are among the largest, most powerful, and most enduring structures in the cosmos. These are not mere fountains of hot gas. They are celestial blowtorches of almost unimaginable scale, firing streams of particles at over 99% the speed of light. They can travel for hundreds of thousands, sometimes millions of light years, extending far beyond the visible boundaries of their own host galaxy, like twin pillars connecting the galactic core to the vast emptiness of intergalactic space. To launch something with such force, with such precision, requires an engine of truly staggering power. Gravity alone, the force pulling everything inward, cannot explain this explosive outward eruption. For years, this was one of astrophysics' greatest puzzles. The solution we discovered lies in a sublime cosmic conspiracy between two fundamental forces: the black hole's immense gravity twisted by its own powerful spin and the invisible but omnipotent influence of magnetism. A supermassive black hole is not a static object. It spins, and because of its incredible mass, it spins with a stability that makes it the universe's most perfect gyroscope. This spin is so profound that it doesn't just turn the object itself. It drags the very fabric of space-time around with it in a cosmic whirlpool, an effect known as frame dragging. Close to the event horizon, space itself is a swirling vortex, a gravitational storm from which nothing can escape. Now introduce magnetism. The superheated plasma of the accretion disk, a sea of charged particles in violent motion, acts as a colossal dynamo. It generates and amplifies magnetic fields to strengths billions of times greater than anything we could produce on Earth. These magnetic field lines rooted in the turbulent disk are then ensnared by the black hole's spinning space-time. Imagine them as invisible elastic bands being twisted tighter and tighter by a furiously rotating motor. They are wound into a tightly coiled tower-like structure that channels the immense rotational energy of the black hole itself. This magnetic tower becomes a cosmic particle accelerator. Charged particles, electrons, and their antimatter counterparts, positrons, are plucked from the innermost edge of the accretion disk and are caught in this violent spinning magnetic field. They are then flung outwards, guided along the black hole's axis of rotation, not by a conventional explosion, but by the relentless organized power of the twisting magnetic forces. They are accelerated to relativistic speeds, forming a coherent narrow beam of pure energy and matter, a jet that will travel across the cosmos for eons. It is a process of breathtaking elegance and violence, converting the rotational energy of a spinning black hole directly into a focused particle beam. This entire celestial engine we came to believe was governed by a principle of profound stability. The key was the black hole's spin axis. Just like a spinning top, the immense angular momentum of a supermassive black hole gives it an extraordinary gyroscopic stability. It would take a cataclysm of almost unimaginable proportions, like a direct head-on merger with another black hole of comparable size, to alter its orientation. Such events are exceedingly rare. Therefore, the spin axis, the very axle upon which the jet-launching engine is built, should remain fixed in space, pointing in the same direction for hundreds of millions, perhaps even billions of years. The jets being locked to this axis were thus seen as cosmic lighthouses, their beams sweeping across the cosmos from a fixed, unwavering position. This stability, this consistency, was not just an elegant theoretical detail. It was a cornerstone of our understanding of how galaxies themselves evolve. These jets are not passive bystanders. As they punch their way out of the galactic core, they act as cosmic sculptors. They slam into the interstellar medium the thin veneer of gas and dust, from which new stars are born, creating immense shockwaves. This violent interaction blows vast bubbles or lobes into the gas surrounding the galaxy, visible to our radio telescopes as ghostly clouds stretching for millions of light years. In some cases, the jet's immense energy can heat up the galaxy's gas reserves, preventing them from cooling and collapsing to form new stars. This process, known as galactic feedback, acts as a cosmic thermostat regulating a galaxy's growth and preventing it from becoming too large too quickly. The jets effectively starve the galaxy of the raw material it needs for star formation. In other instances, the shockwave from a jet can compress gas clouds, triggering a burst of new star formation in its wake. The jets are therefore both creators and destroyers on a galactic scale, the primary tool by which the central engine communicates its power to its vast stellar empire. They dredge up heavy elements forged in the accretion disk and distribute them into the intergalactic medium, seeding the next generation of galaxies. The evidence for their long-term stability was written all around us. We could see the colossal radiolobes perfectly aligned on either side of a galaxy, clear evidence of a jet that has been firing in the same direction for an immense span of time. We could trace the paths carved through galactic clusters, tunnels bored through the hot X-ray emitting gas by a jet that had been relentlessly pushing forward for ages. Everything we saw, from the physics of the central engine to the large-scale structures in the universe, pointed to this same unambiguous conclusion. The orientation of a black hole's jet was a fixed property, a permanent feature as fundamental as the black hole's mass itself. It was the galaxy's North Star, an immovable axis that dictated the flow of energy and the course of galactic evolution over deep time. We constructed our models around this certainty. We built our simulations upon this foundational assumption. It was a beautiful, complete and powerful picture of the universe, one where the most chaotic regions gave rise to the most stable and enduring structures. This paradigm of the unwavering cosmic lighthouse became a pillar of modern astrophysics, a truth we thought was etched into the very fabric of space-time. A story whose beginning, middle and end we were confident we finally understood. We believed we had solved the puzzle of the black hole's creative fury. We were wrong, and so we had painted a portrait of majestic stability, a picture of galactic engines, billions of solar masses strong locked into their cosmic purpose. These supermassive black holes with their spinning accretion disks acting as immense gravitational gyroscopes were thought to be the most steadfast objects in the universe. Their jets, those colossal beams of energy, were the very symbols of this permanent celestial monuments, fired across the eons, unwavering and true. For decades, this model of serene and predictable power was the bedrock of our understanding, a reassuring constant in a cosmos teeming with chaos. It was a beautiful theory. It was elegant. And like so many beautiful things in science, it was hiding a profound and unsettling secret. The first clues were never a sudden cataclysmic discovery, a single photograph that overturned everything. They arrived as all true cosmic mysteries do, not with a bang, but as a whisper. A quiet accumulation of oddities, a gallery of cosmic portraits that just didn't look quite right. These whispers began in the quiet, data-filled rooms where radio astronomers spent their lives staring into the deep. They were looking at radio galaxies, those magnificent beasts whose jets scream so loudly in the radio spectrum that they can outshine their entire host galaxy. According to the standard model, the jets should be gloriously, almost geometrically perfect. Two straight narrow cones of plasma punching out of the galactic core in opposite directions like twin lances hurled by a god. And many of them were. We saw them, mapped them, and catalogued them, each one a testament to the elegant physics of the accretion disk. But scattered amongst these paragons of symmetry were the weird ones, the mavericks, galaxies like 3C315, whose jets, instead of being straight, were bent into a gentle sweeping C shape. Or others that displayed a subtle but undeniable S, curve, a work of celestial calligraphy, scribbled across a canvas hundreds of thousands of light-years wide. At first, these were easily dismissed. We had ready-made explanations, tidy theories that could account for these gentle asymmetries without disturbing our core beliefs about the central engine. Perhaps we argued the galaxy itself was moving. As the host galaxy ploughs through the thin, almost imperceptible gas of the intergalactic medium, its jets would be blown back, like the smoke from a moving steam train's smokestack. This ram pressure could easily create a C shape. It was a perfectly plausible explanation, an external force acting upon an otherwise stable system. The central engine remained a perfect gyroscope. The universe was just giving its exhaust plume a little push. For the S-shaped galaxies, we had another clever idea procession. Not of the black hole's spin axis itself that was considered far too stable, too massive to be easily perturbed, but of the accretion disk. Perhaps a companion galaxy in a slow gravitational dance was gently torquing the disk, causing it to wobble like a spinning plate. This wobble would in turn cause the jets to slowly change their direction, carving a graceful spiral or a pattern over millions of years. This too kept the heart of the machine, the black hole, pristine and stable. The anomalies were merely the result of local environmental factors, cosmic weather patterns that sculpted the jets after they had been launched. The engine was fine. The problem was with the terrain. For a long time, these explanations held. They were logical, they fit much of the data, and they protected the central paradigm. But the universe is patient, and it has a way of revealing its deeper truths to those who are willing to keep looking. As our telescopes grew more sensitive as projects like the Very Large Array in New Mexico began to stitch together radio images of unprecedented clarity, the gallery of oddities grew. And the explanations began to wear thin. We found jets that were bent too sharply too close to the galactic core for ram pressure to be the sole culprit. The push from the intergalactic medium should be a gentle, large-scale effect, yet we were seeing kinks and twists that seemed to originate much deeper within the galaxy's gravitational well. We found X-shaped radio galaxies a truly bizarre configuration. These cosmic enigmas displayed not one but two pairs of misaligned lobes. There was a primary active pair, bright and vibrant, being fed by the current jets. But then there was a second, often fainter, and larger pair oriented at a completely different angle, looking for all the world like a ghostly echo of a previous eruption. What could cause such a structure? Was it two black holes in a tight binary orbit, each firing off its own set of jets? Was it a jet that had somehow been deflected and split? Or was it something far more profound? The S-shaped galaxies also began to present deeper puzzles. The precession model was elegant, but it required a specific set of circumstances, a companion galaxy of the right mass in the right orbit, to gently torque the disk over millions of years. Yet we found these sinuous jets in galaxies that appeared to be utterly isolated cosmic hermits, with no dance partner in sight. The smooth, predictable wobble of precession struggled to account for the jarring, almost violent changes in direction seen in some systems. These weren't graceful curves, they were jagged cosmic graffiti. Each new observation, each peculiar galaxy added another small weight to the scales of evidence. Individually, any one of them could be explained away perhaps as a unique 1 in a billion alignment of circumstances. But collectively they started to paint a picture of systemic unease. The comfortable, steadfast model of a stable gyroscopic engine was beginning to fray at the edges, strained by a growing catalogue of cosmic exceptions. The whispers of inconsistency were growing louder, evolving from a murmur in the background to a nagging question that haunted late-night observing runs and fueled passionate debates at scientific conferences. Was the universe messier than we thought, or was our model simply wrong? The tension escalated when we began to look not just at the shape of these jets, but at their behaviour over time. If the shape gave us a snapshot, a single frame in a cosmic movie, then studying their brightness variations, their flickering could reveal the dynamics of the engine itself. For this, astronomers turn their gaze to a special class of active galactic nuclei known as blazars. Blazars are a matter of perspective. They are simply quasars or radio galaxies where, by sheer cosmic chance, one of the jets is pointed almost directly at us. Looking down the barrel of a particle accelerator, billions of light years long, is a truly extraordinary experience. The light from this jet is so intensely beamed and amplified by relativistic effects that it can outshine the entire host galaxy 1,000 times over, making it one of the most luminous and violent phenomena we can observe. They are cosmic lighthouses, and their beams are not steady. They flicker, they flare, they vary in brightness on timescales from years down to mere hours. For a long time we believed we understood this variability. The standard model posited that shocks like sonic booms were propagating down the jet's length. As these shocks compressed the plasma and magnetic fields, they would cause regions of the jet to glow brightly, creating the flares we observed. This model was powerful. It could explain the general character of the flickering, the rise and fall of brightness as these shock fronts travelled down the jet, moving at over 99% of the speed of light. It was a model of controlled chaos of predictable instabilities running through a fundamentally stable outflow. The jet itself was a constant river. We were just seeing the ripples on its surface. But as our monitoring campaigns became more sophisticated, as robotic telescopes began to watch these cosmic beacons night after night, year after year, the data started to tell a more complicated story. The flickering wasn't always so predictable. We saw flares that rose and fell faster than the light travel time across the presumed size of the emitting region, a paradox that seemed to violate the laws of physics, unless the source was extraordinarily compact, far smaller than the shock models predicted. We saw quasi-periodic oscillations, or QPOs, a subtle rhythmic pulse, hidden within the chaotic noise of the blazer's light curve like a faint drumbeat in a thunderstorm. A shock wave propagating down a jet shouldn't have a rhythm. It should be a random stochastic process. A pulse, however, hints at something else. It hints at a clock. And the only clock at the heart of the galaxy with that kind of precision is the material orbiting the black hole itself. These rhythmic signals were maddeningly elusive. They would appear for a few cycles holding a steady tempo, only to vanish back into the noise, leaving astronomers to wonder if they had seen a true signal or just a statistical ghost. Was this the signature of a hotspot, a single bright clump of matter, orbiting in the innermost regions of the accretion disk, its light being beamed towards us with every rotation? If so, it was a direct probe of the engine room, a way to measure the spin of the black hole and the physics of matter at the very edge of oblivion. The implications were staggering, but the data was tantalizingly inconclusive. For every team that published a paper claiming the discovery of a QPO, another would publish a rebuttal arguing it was just random noise masquerading as order. The debate raged, pushing our instruments and our analytical techniques to their absolute limits. We were trying to decipher the heartbeat of an engine from billions of light years away through the fog of intergalactic space and the shimmering of our own atmosphere. The signal was faint, the noise was deafening, and the stakes were immense. The very nature of the central engine hung in the balance. Then came the truly bizarre observations, the ones that defied easy categorization. We found blazers that seemed to turn off their immense radio jets, fading to a mere trickle over the course of only a few years, a cosmic eye blink. A stable, massive gyroscopic system powered by a constant rain of matter shouldn't just shut down. It would be like a star extinguishing itself overnight. Conversely, we saw galaxies that were quiet for decades suddenly roar to life, their cores flaring up and launching the beginnings of a new jet. These changing look quasars were a direct challenge to the idea of a steady-state accretion process. They suggested that the flow of fuel onto the black hole was not a smooth, continuous river, but a clumpy, chaotic and unpredictable deluge. This lumpy accretion could perhaps explain the flickering brightness, but it opened up a whole new can of worms. If the fuel supply was so erratic, could it affect the stability of the disk itself? Could a sudden influx of matter arriving at the wrong angle be enough to physically jolt the spinning disk to alter its orientation? The questions were piling up, and the simple model of a stable gyroscope looked increasingly naive. It was like trying to understand the Earth's weather by assuming the planet is a perfectly smooth, featureless sphere. We were beginning to realize that the devil was in the details, and the details were becoming overwhelmingly complex. The most damning evidence, however, came not from the living jets, but from the dead ones. To find it, we had to become cosmic archaeologists digging through the layers of radio emissions to uncover the history of these galactic monsters. When a jet pumps energy into the void, it doesn't just disappear. It inflates vast, ghostly bubbles of plasma and magnetic fields far outside the visible confines of the galaxy. These are the radiolobes, some of which can swell to be millions of light years across, dwarfing the galaxies that created them. These lobes are the jet's legacy, a lingering testament to its power, and they can persist for hundreds of millions of years after the jet itself has shut off, slowly fading like the embers of a colossal fire. Using low-frequency radio telescopes, which are particularly sensitive to these older, more diffuse structures, astronomers began a systematic search for these fossil jets, and what they found was breathtaking. They found galaxies with an active bright jet slicing through space in one direction, while surrounding it like a ghostly shroud were the faint dying remnants of a much older pair of radiolobes, oriented in a completely different direction. This was the smoking gun. This was not a subtle curve or a mysterious flicker. This was the cosmic equivalent of finding two sets of footprints in the snow heading in opposite directions from a single point. It was an unambiguous historical record, written in colossal letters across the sky, that the central engine's axis of rotation had not been stable. It had at some point in its past undergone a dramatic and profound reorientation. The galaxy NGC 326 provided a stunning example. Its active jets trace a beautiful S-shape, a classic sign of slow precession. But surrounding this structure are enormous faint outer lobes that tell a different story. They show that hundreds of millions of years ago, the jet axis was pointed somewhere else entirely. The engine had not just wobbled, it had fundamentally realigned itself. Another object, a galaxy cluster named Able 2626, revealed an even more complex history. Its central galaxy hosts not 2, not 4, but 6 ghost cavities, 6 bubbles blown by jets at 3 distinct times, each pair pointing in a different direction. It was a chronicle of cosmic chaos, a history of an engine that had been violently thrown off balance at least twice in its past. These ghostly relics presented a severe, almost fatal challenge to the established paradigm. The gentle push of interglacial wind couldn't account for a 90-degree flip. The slow, graceful waltz of disk precession struggled to explain such violent episodic changes. These observations were telling us that something far more fundamental, something deep within the engine room itself, was capable of catastrophic instability. The gyroscopic heart of the galaxy was not a steadfast anchor. It was a machine that could be jolted, tilted, and completely reconfigured. The meticulous process of gathering this data had taken decades. It required building bigger and better telescopes, developing new imaging techniques, and having the patience to stare at the same patch of sky for thousands of hours, waiting for the universe to give up its secrets. Each anomalous galaxy, each strange light, curve, each fossil lobe was a single data point, a breadcrumb on a trail leading away from comfortable certainty and toward a new, unsettling frontier. The tension between theory and observation had reached a breaking point. The whispers of cosmic unease had grown into a roar. The evidence was now undeniable. The jets were not stable. They could move. They could wobble. They could even, it seemed, completely change their minds. But that raised the ultimate question, the one that would set the course for the next revolution in astrophysics. It wasn't enough to know that the jets moved. We had to know why. What force, what mechanism, what cataclysmic event could possibly be powerful enough to reach into the heart of a galaxy and physically tilt the axis of a monster, spinning with the energy of 1 billion suns? The answer would force us to reconsider the very nature of black holes themselves. And so the evidence began to mount piece by tantalizing piece. Across the cosmos we had found the celestial crime scenes, galaxies scarred with colossal X-shaped radio signatures, ancient ghostly lobes of gas telling a silent story of jets that once pointed in a completely different direction. These were the tantalizing clues, the cosmic breadcrumbs that hinted at a profound and unsettling truth. But they were ghosts of a past cataclysm, not the act itself. To truly shatter the paradigm, astronomers needed more. They needed to catch a black hole in the very act of this unthinkable reorientation. They needed a smoking gun. For years, the hunt yielded nothing but deeper frustration. The universe in its infinite majesty guards its most violent secrets with a patience we can barely comprehend. The timescales involved are stupefying. A human lifetime is less than a single tick of the clock that governs the heart of a galaxy. Expecting to witness such a monumental shift seemed to many a fool's errand. The prevailing wisdom held firm the spin of a black hole, that gravitational gyroscope anchoring an entire galaxy was immutable, fixed for eternity. The anomalies we observed must be optical illusions or the complex results of interacting gas clouds, anything but what they appeared to be, anything but a black hole fundamentally changing its mind. The search, however, is humanity's driving force, and it led a dedicated team to a distant, unassuming galaxy. Catalogued as PBC J23 3.92343, it was a giant radio galaxy, one of billions, nearly 1 billion light-years from Earth. It was a mere pinprick of ancient light in the constellation Cetus. But this particular galaxy had a strange pulse. It whispered of a story, of violent recent history. Earlier radio surveys, like our maps of the X-shaped phantoms, showed 2 enormous aging lobes of plasma stretching out for over 1.5 million light-years, far larger than the Milky Way itself. They were the fading embers of a stupendous ancient eruption, a testament to the black hole's power from a bygone era. These lobes were precisely what we expected to see. But something was wrong. Closer to the galactic core, the heart of the beast, newer radio data from the Very Large Array in New Mexico painted a picture of startling contradiction. Two much younger, much brighter jets of material were present, but they were not aligned with the ancient ghosts. They were not even slightly misaligned. They were pointed in an entirely different direction, almost 90 degrees away from their colossal predecessors. It was as if a lighthouse had been ripped from its foundations and bolted back on facing an entirely new sea. This was more than an anomaly. It was a glaring inconsistency, a direct challenge to everything we thought we knew. The initial reaction within the small team of astrophysicists was not excitement, but a deep professional skepticism. A discovery of this magnitude invites extraordinary scrutiny first and foremost from the discoverers themselves. Dr. Lorena Hernandez, the lead radio astronomer on the project, remembers the moment the first composite image resolved on her screen. The faint, sprawling ancient lobes in one orientation, and the bright, tight, energetic new jets in another. It was a picture of impossible physics, a paradox in light. The first thought is never eureka. The first thought is always, what did we do wrong? Every calculation was checked, every line of code re-verified. The telescopes were recalibrated, the observations repeated. Could there be two separate supermassive black holes at the core, each with its own jet, creating this bizarre illusion? The data from optical and infrared telescopes was combed through, searching for the gravitational telltale signs of a binary system. Nothing. There was only one gravitational anchor, one monstrous engine at the heart of PBC J2333.92343. One black hole somehow responsible for two distinct perpendicular eruptions separated by millions of years. The team knew that radio waves, while powerful, only told part of the story. Radio astronomy shows us the grand, sweeping aftermath, the energetic plasma, as it cools and expands over eons. To see the engine room itself, to witness the fresh violence spewing directly from the accretion disk in real time, you need to see the universe in a different, more ferocious light. You need to see an X-rays. They turned to NASA's Chandra X-ray Observatory, a magnificent orbiting telescope designed to detect the highest energy phenomena the cosmos has to offer. If new jets were actively being powered, their point of origin would blaze with X-ray radiation, the signature of matter being heated to millions of degrees just before its final desperate plunge into the event horizon. The request for observation time was granted, and Chandra turned its sensitive eye towards the distant galactic core. For weeks the observatory stared, unblinking, collecting the faint high-energy photons that had journeyed for nearly 1 billion years to reach its detectors. Down on Earth the team waited. The data streamed in packet by packet from orbit, slowly building an image of something no human had ever seen before. And then, it was there. The moment of revelation. The moment an entire field of astrophysics was forced to hold its breath and confront a terrifying new reality. The Chandra data was unequivocal, sharp, and brutally clear. It showed two brilliant focused streams of X-ray light perfectly aligned with the new younger radio jets. They were not artifacts. They were not illusions. They were active, ongoing eruptions from the galactic nucleus. They were the celestial blowtorch caught in the act. And they were pointed directly, undeniably sideways, completely ignoring the grand ancient structures that testified to the black hole's former orientation. The ghost and the machine captured in a single frame, the faint radio whispers of the past and the brilliant X-ray scream of the present. And they were turned at right angles. It was incontrovertible. It was the smoking gun. The shock wasn't a sudden cinematic gasp. It was a slow, dawning, chilling silence that fell over the control room as the final composite image loaded. There on the screen was the physical embodiment of a scientific heresy. The bedrock idea of a black hole's rotational stability, a concept that underpinned countless theories of galaxy formation, was not just cracked. It was shattered. It was like discovering that the Earth's North Pole could spontaneously leap to the equator. It was a violation of a sacred cosmic order. The implications began to wash over the scientific community like a series of relentless aftershocks. The first was one of profound disbelief. When Hernandez and her team submitted their paper, the peer review process was intense, even adversarial. Reviewers tore through the methodology, questioned the data, and proposed every conceivable alternative explanation. Was it a chance alignment? A trick of galactic dust? A previously unknown phenomenon mimicking a jet? but the evidence was too robust, the multi-wavelength data from radio to X-ray too perfectly synchronized. The data held. The conclusion was inescapable. The black hole's jet had flipped. Suddenly all those other oddities, those X-shaped galaxies that had been dismissed as peculiar exceptions, snapped into focus. They weren't exceptions. They were signposts pointing to this fundamental chaotic process. They were the rule, not the exception. We had been looking at the evidence all along, but we couldn't bring ourselves to believe what it was telling us. The universe we thought we knew, at least in its grandest structures, had a foundational stability. Galaxies, we believed, evolved slowly majestically, their central engines spinning like perfect tops for billions of years. This discovery tore that serene tapestry to shreds. It replaced it with a vision of the cosmos that was far more violent, more unpredictable, and infinitely more interesting. Imagine the effect this has on a galaxy's evolution. For millions of years, the supermassive black hole acts like a focused weapon, blasting a jet of energy deep into the intergalactic medium in one direction. This jet carves out vast cavities in the surrounding gas, heating it up and preventing it from cooling and forming new stars. The galaxy's growth in that direction is effectively choked off, but now we understood that the weapon could be retargeted. In a cosmological instant, the jet shuts down, and a new one erupts in a completely different direction. It's no longer a focused blowtorch. It's a cosmic sprinkler system of cataclysmic energy, spraying death and creation across vast swathes of its host galaxy over the course of its lifetime. One region is sterilized of star-forming gas, while another, previously untouched, is suddenly blasted by a torrent of relativistic particles. This process doesn't just nudge galactic evolution, it violently redirects it. It rewrites the rules for how galaxies breathe, how they grow, and how they ultimately die. The revelation from PBC J23 233 forced us to re-examine everything. Every galaxy with a strange morphology, every misaligned radio lobe was now seen through this new revolutionary lens. It was as if we had been trying to read a library of ancient books, unaware that a key chapter had been torn from every single one. Now, with that missing chapter restored, the stories of these galaxies began to make a terrifying kind of sense. The universe was not a place of elegant, predictable gyroscopes. It was a place of chaos, of stupendous, world-altering collisions, and forces so great they could physically tilt the axis of a spinning monster millions of times more massive than our sun. The stability we had projected onto the heavens was an illusion born of our own fleeting existence on a quiet cosmic shore. In the deep ocean, the storms rage with an intensity we are only now beginning to comprehend. We had found our undeniable proof. We had witnessed the ghost of an old orientation, and the living fury of a new one born from the same cosmic heart. The shock gave way to a thrilling, terrifying awe. We had overturned a pillar of astrophysics, but in doing so we had unlocked a mystery far deeper, far more profound than the one we'd set out to solve. The evidence on the screen was absolute. It showed us what happened. The jet had flipped, but it gave us no clue as to the single most important question that followed. It gave us no hint of the culprit. What titanic force, what unimaginable cosmic event could possibly be powerful enough to reach into the heart of a galaxy and wrench the spin axis of a supermassive black hole? What could shatter a gyroscope that weighs as much as 1 billion suns? The search for the smoking gun was over. But the hunt for the force that pulled the trigger had only just begun. The discovery was not a quiet revelation whispered in the hallowed halls of academia. It was a thunderclap, a seismic shock that resonated through the entire field of astrophysics. In control rooms and data centers across the globe, what had been the thrill of discovery quickly morphed into a profound and unsettling state of intellectual vertigo. The data was unambiguous, the event undeniable. A supermassive black hole, a cosmic engine we thought we understood, had done something impossible. It had flipped its poles, reversing the flow of its colossal jets of plasma, as casually as a child might reverse the direction of a spinning top. But this was no toy. This was a gravitational titan millions of times the mass of our sun, and its behavior had just torn a gaping hole in our most fundamental theories. The immediate aftermath was a storm of frantic communication, a digital flood of emails and preprint papers, as theorists scrambled not just to find an answer, but to even frame the right questions. How could something anchored by such immense gravity, a linchpin of its entire galaxy, exhibit such a violent and shocking instability? It was as if the North Pole of Earth had suddenly appeared over Antarctica, not through a slow geological drift over eons, but in the span of a single lifetime. The laws of physics, particularly the conservation of angular momentum, seemed to scream that this could not happen. A black hole's spin is its most defining characteristic beyond its mass. It is a cosmic gyroscope, a source of stability so profound that it warps the very fabric of space-time around it into a swirling vortex. This spin axis should be unyielding, fixed in space for eternity. Yet here was the evidence etched in the ghostly trails of radio emissions stretching across hundreds of thousands of light-years, a complete 90-degree reorientation. The textbooks filled with elegant diagrams of stable, predictable accretion disks and unwavering jets were suddenly frighteningly incomplete. The first wave of explanations centered on the one component of the system that possessed a degree of theoretical flexibility, the accretion disk. This is the lifeblood of the black hole, a vast swirling platter of gas dust and shredded stars spiraling inward to its doom. For decades our models had depicted this disk as a relatively orderly affair, a cosmic vinyl record spinning smoothly on the turntable of the black hole's gravity. The gas we believed would settle into the black hole's equatorial plane, aligning itself perfectly with the Leviathan's spin. From this stable, rotating platform, magnetic field lines twisted into tight funnels would then launch the jets out from the poles straight and true. It was a neat, tidy and powerful model that explained so much of what we saw across the universe. But what if the record on the turntable was warped? This was the first port of call for stunned theorists. The idea known as the Bardeen-Peterson effect was not entirely new. It explored a mind-bending consequence of Einstein's general relativity known as frame dragging, or the Lens-Thirring effect. The theory posits that a spinning black hole doesn't just sit in space-time, it actively drags space-time around with it like a spinning ball, submerged in honey drags the viscous liquid along for the ride. If a cloud of gas were to fall toward the black hole at a skewed angle, colliding with the existing disk from a different plane, it wouldn't simply merge and settle down. Instead, this titanic collision of cosmic material would create a conflict, a war between the momentum of the infalling gas and the irresistible twisting of space-time. The inner part of the disk closest to the black hole would be violently torqued by frame dragging, forced to align with the black hole's equator, but the outer part farther away and less influenced by the space-time swirl would stubbornly retain its original tilted orientation. The result is no longer a flat, elegant disk. It becomes a warped, twisted structure, a contorted ribbon of superheated plasma. This warped disk would not spin smoothly. It would precess. Imagine that wobbling top again. As it spins, its axis slowly carves a circle in the air. In the same way, this warped disk would wobble its entire structure, slowly changing its tilt under the complex gravitational and relativistic forces at play. And if the jets are launched from the very centre of this disk, from the region most tightly coupled to the black hole's spin, then as the disk wobbles, shouldn't the jets wobble with it? This was the first plausible mechanism. The idea was tantalising. It used known physics, it involved the dynamic environment we knew to exist around these behemoths, and it provided a way to change the jet's direction. Supercomputer simulations were spun up immediately, programmers feeding these complex relativistic equations into digital universes. They watched as virtual clouds of gas were thrown at spinning black holes, observing the formation of these beautiful, impossible warped structures. In these simulations, the innermost region of the disk, the launch pad for the jets, did indeed begin to process its orientation, tracing a slow, graceful circle over millions of years, and for a moment it felt like the crisis might be averted. The model showed the jets would follow, sweeping across the sky like a celestial lighthouse beam. But then scientists laid the simulations alongside the cold, hard data from the galaxy, and the theory began to fray. The problem was one of time and temperament. The precession of a warped disk, while dramatic, is a relatively gentle, predictable process. It is a slow wobble, a graceful dance that unfolds over timescales of millions of years. The data from our rogue galaxy told a very different story. The jets hadn't wobbled. They hadn't drifted. They had snapped. The reorientation was violent, sudden, and complete. The timescale was not millions of years, but likely a few thousand, maybe less. An eye blink in cosmic terms. A gentle wobble could not account for this cataclysmic break. It was the difference between a river slowly changing its course over centuries and a dam bursting in a single catastrophic moment. The warped disk model, so elegant in its conception, couldn't provide the necessary force or the required speed. It was a piece of the puzzle, perhaps, but it was not the whole picture. The community was forced to confront a far more radical, far more chaotic possibility. The problem might not be with the fuel source, the accretion disk. The problem might be with the engine itself. What if there wasn't one? The new hypothesis that emerged from the theoretical ferment was breathtaking in its scale. It proposed that at the heart of this galaxy there was not a lone supermassive black hole, but a pair of them locked in a deadly gravitational embrace. We know that galaxies collide and merge all the time. It is the primary way they grow and evolve over cosmic history. And when two galaxies merge, their central supermassive black holes should over hundreds of millions of years sink toward the new galactic center, eventually finding each other to form a binary system. Two titans, each millions or even billions of times the mass of our Sun, orbiting a common center of gravity. The very thought is almost too much to comprehend. It would be the most extreme environment in the known universe. Their orbital dance would not be a graceful waltz. It would be a maelstrom. Here, gravity is not a gentle guiding force. It is a violent, churning, unpredictable force. The two behemoths would stir the surrounding gas into a chaotic frenzy, carving out vast empty lanes and flinging streams of stars across the galaxy like cosmic graffiti. And in this scenario, the stability of a single well-behaved accretion disk becomes a fantasy. The gravitational influence of the second black hole, the perturber, would be a constant disruptive hammer blow to the disk of the primary jet-emitting black hole. As the secondary black hole swung by on its orbit, its gravity could rip, tear, and tilt the primary's disk with shocking violence. It could even in the most extreme models exert enough gravitational torque not just on the disk, but on the primary black hole itself. Think of it not as a wobbling top, but as a gyroscope being struck by a sledgehammer. The secondary black hole's repeated gravitational kicks could over time destabilize the primary black hole's spin axis, causing it to precess wildly and erratically. It could even, if the orbital mechanics were just right, cause the axis to undergo a complete and rapid flip. This was a model born of pure chaos, but it had one major advantage over the warped disk theory. It was violent enough to match the observations. The timescale of a binary black hole's orbit could be on the order of thousands of years, a near-perfect match for the inferred speed of the jet flip. The gravitational forces involved were more than sufficient to explain the sheer energy of the event. The digital universes inside the supercomputers were reconfigured. Now they weren't modelling a single black hole, but two, a dizzying dance of relativistic gravity. The simulations were mesmerizing, a symphony of destruction and creation. They showed the companion black hole plunging through the accretion disk of the primary, sending shockwaves of incandescent gas rippling outwards. They showed the disk being torn apart with streams of material being siphoned from one monster to the other. And they showed that under certain conditions the primary black hole's spin axis could indeed be sent tumbling its jets, flailing wildly across the simulated cosmos before settling into a new, completely reversed orientation. The binary model seemed to work. It was messy, it was complex, but it carried the whiff of truth, because it embraced the sheer violence of the cosmos. The community was buzzing with this new terrifyingly beautiful idea. But it also carried an immense burden of proof. If this hypothesis were true, if the flip was caused by a gravitational partner in crime, then that partner must still be there, orbiting silently in the dark. Where was the second black hole? Finding a supermassive black hole that is actively feeding and powering jets is one thing. Its blazing accretion disk acts as a beacon. But finding a quiescent silent partner, a black hole that is not actively feeding, is an astronomical challenge of the highest order. It would be an invisible titan detectable only by the subtle gravitational tug it exerts on the stars and gas around it. The intense debate that erupted was not just about which theory was correct. It was a fundamental clash of philosophies. Was the universe at its heart a place of order and predictability where events like this could be explained by the gentle evolving physics of a single object? Or was it a place of chaos and contingency, where the most dramatic events were driven by rare violent encounters between cosmic titans? The warped disk theory was a vote for order, the binary black hole theory was a vote for chaos, and the implications stretched far beyond this one peculiar galaxy. Black hole jets are not just cosmic light shows, they are fundamental agents of cosmic evolution. They are the feedback mechanism that regulates the growth of entire galaxies. Their powerful outflows blast through the galactic disk, heating up gas and preventing it from collapsing to form new stars. They are the reason why the largest galaxies in the universe are not filled with brilliant young blue stars, but are instead red and dead, their star-forming days long behind them. We had built entire models of galaxy formation around the idea that this feedback was consistent, that jets would plough into their host galaxies from a stable, predictable direction for eons. But if jets can flip, if they can suddenly and violently change their direction, then our entire understanding of this cosmic regulatory system is thrown into question. A jet that once blasted out into the empty intergalactic medium could suddenly turn and scythe through the densest part of its own galactic disk, triggering furious bursts of star formation in some regions, while sterilizing others completely. It would be an unpredictable, chaotic process rewriting the history and destiny of a galaxy on a timescale of millennia. This one observation had created a domino effect of uncertainty cascading through astrophysics and cosmology, toppling cherished assumptions one by one. The frenzy of theoretical work was exhilarating, a testament to the agility of the human mind when faced with a profound mystery. But these were just stories, elegant mathematical narratives written on whiteboards and computer code. They were ghosts in the machine, plausible phantoms haunting the data. To distinguish between them, to move from speculation to understanding, theorists could only take us so far. The models had given us a roadmap of possibilities, a gallery of cosmic suspects, each with a motive and a method. But to solve the crime, we would have to return to the scene. We would need to gather more evidence to search for the clues that would vindicate one theory and condemn the others. The challenge was no longer one of imagination, but of observation. How can we possibly peer into the chaotic heart of a galaxy, hundreds of millions of light years away, and find the smoking gun? How do you prove the existence of a warped disk, or find an invisible black hole when it is shrouded in a veil of gas and dust, and dwarfed by the glare of the very cataclysm it has created? And so we are left suspended staring at an impossible cosmic crime scene. The evidence is etched in radio waves across millions of light years. The weapon, a colossal jet of elementary particles. But the motive, the mechanism, the sheer physical means by which a galaxy's most fundamental axis of power can be torn from its foundations and violently reoriented remains a profound and unsettling mystery. To solve it, we must journey past the shimmering event horizon of our understanding and into the warped, twisted reality that surrounds a spinning supermassive black hole. We must venture into a realm where space and time are no longer passive bystanders, but active, malevolent participants in the cosmic drama. Here in the gravitational abyss, two prime suspects await our interrogation. One is a force of insidious grinding persistence, a slow poison working over millennia. The other an agent of unimaginable violence, a cataclysm that rewrites the laws of a galaxy in a single thunderous instant. Our first line of inquiry leads us to one of the most bizarre and mind-bending predictions of Einstein's theory of general relativity. It is a concept so counterintuitive that Einstein himself was skeptical. It's called the Lens-Thirring effect, or more evocatively, frame dragging. To grasp its power, you must first discard your everyday notions of space. Imagine space-time not as an empty stage, but as a thick, viscous fluid, a cosmic treacle that permeates everything. Now place a massive object into this fluid. If it is stationary, it merely sinks, creating a smooth, symmetrical depression we call a gravity well. This is the simple gravity of our sun or a non-spinning black hole. But what happens if that object is spinning and spinning with the furious velocity of a supermassive black hole, its equator moving at a significant fraction of the speed of light? The answer is the key. The spinning behemoth doesn't just sit in the space-time fluid, It grabs it, twists it, and forces it to rotate along with it. Close to the event horizon, this dragging effect is overwhelming. Space-time is caught in a furious, inescapable vortex, a whirlpool more powerful than any current, from which not even light can travel in a straight line. This is not merely an abstract mathematical curiosity. It is a physical, tangible distortion of the universe. It is as real as the ground beneath your feet. A gyroscope sent into this region would find its axis of rotation mercilessly torqued, forced to precess and align with the black hole's own spin. The very definition of straight and still is erased, replaced by a swirling compulsory dance dictated by the central engine. For anything unlucky enough to be caught in this gravitational storm, resistance is futile. Now let us place our accretion disk into this chaotic environment. This vast incandescent platter of gas dust and shredded stars is the fuel that powers the jets. Imagine that through some past cosmic event, perhaps the capture of a giant gas cloud from a different angle, this disk settles into an orbit that is misaligned with the black hole's equatorial plane. The disk wants to orbit on one plane, but the black hole is spinning on another. It's an unstable, untenable arrangement, a cosmic misalignment waiting for a correction. And the Lens-Thirring effect is the universe's brutally efficient chiropractor. The inner edge of the disk, the part closest to the churning abyss, feels the frame-dragging effect most acutely. The space-time it inhabits is being twisted with irresistible force. This relentless gravitational torque acts like a cosmic wrench, grabbing the inner ring of the disk and physically twisting it, wrenching it out of its original orientation, and forcing it to align with the black hole's equator. The innermost region of the accretion disk simply has no choice. It snaps into alignment, creating a severe warp between this newly aligned inner section and the still misaligned outer regions. This is where the true power of the theory reveals itself. The alignment does not happen all at once. Instead, a wave of alignment is born. This wave, a propagating warp in the very structure of the disk, begins to move outwards from the center. You can visualize it as a ripple, not of water, but of space-time geometry itself spreading through the incandescent material. As this wave propagates, it communicates the black hole's spin orientation to the rest of the disk section by section. Like a line of falling dominoes, each successive ring of gas and dust feels the torque from its inner neighbor, succumbs to the gravitational mandate and twists into the new alignment. Over thousands, perhaps hundreds of thousands of years, this wave of realignment marches relentlessly outwards through the disk. The process is a slow, grinding and inexorable transformation. It is the universe smoothing out an imperfection through the sheer brute force of gravity. And what of the jets? The jets, we must remember, are born from the twisted magnetic fields anchored in the very innermost part of the accretion disk, the part most intimately connected to the black hole's spin. They are launched perpendicular to this inner disk region. So as the inner disk is torqued and twisted by frame dragging, the launch pad for the jets is also being twisted. The magnetic anchor points are being dragged along for the ride. Consequently, the jet itself, this pillar of light and energy stretching across a galaxy, is forced to change its direction. As the inner disk slowly precesses, wobbling like a dying top, and settles into its new alignment with the black hole's equator, the jet dutifully follows its lead. The colossal beam of energy, millions of light-years long, is steered across the heavens not by some external force, but by the subtle yet irresistible twisting of space-time at its very heart. In this model, the flipping of a jet is not a sudden event. It is the final dramatic outcome of a long drawn-out gravitational ballet. We, with our fleeting astronomical observations, might only catch the final act, witnessing what appears to be a sudden 90-degree shift. But the Lens-Thirring model tells us we are merely seeing the culmination of a process that has been unfolding in the dark for eons. The entire system, from the event horizon to the outer disk, has been engaged in a colossal gravitational argument, and the spin of the black hole has finally and definitively won. The jet's new direction is simply a declaration of that victory. It is an elegant, compelling, and deeply physical explanation. It relies on nothing more than gravity, gas, and time. It paints a picture of a universe that constantly seeks equilibrium, even if it must bend the fabric of reality itself to achieve it. But is this slow, methodical process the only answer? The universe is rarely so gentle. For every process of slow erosion there is an earthquake. For every graceful dance there is a violent collision. Our second suspect offers no such elegance. It proposes that the reorientation of a black hole's jet is not a negotiation. It is the result of a hostile takeover of the most extreme kind. To understand this alternative, we must confront a reality that astronomers are only now beginning to fully appreciate galaxies merge, and when they do, their central supermassive black holes, once the undisputed rulers of their own domains, are set on an unavoidable collision course. For millions of years they will orbit one another in a majestic decaying spiral. Imagine two of these monsters, each weighing billions of times the mass of our Sun, locked in a gravitational death dance. They are not merely 2 points of mass. They are two spinning, space-time dragging behemoths, each with its own accretion disk, its own history, its own angular momentum. As they draw closer, the tidal forces become apocalyptic. Entire star clusters are flung out into intergalactic space. The accretion disks are warped, shredded, and cannibalized. The dance becomes faster, more frantic, a chaotic maelstrom of gravity and energy at the heart of the newly merged galaxy. In the final moments of this cosmic waltz, the physics becomes almost too extreme to comprehend. The two black holes are now moving at a substantial fraction of the speed of light, whipping around each other multiple times per second. They are distorting not just the space-time around them, but each other. Their event horizons, the very surfaces of no return, are stretched and deformed into teardrop shapes by the immense tidal forces. The space between them churns into a gravitational tempest, and from this storm, a tsunami is unleashed upon the universe. This is a blast of gravitational waves, pure ripples in the fabric of space-time, carrying away an amount of energy so vast it momentarily outshines all the starlight in the observable universe combined. This is the inspiral and merger phase, the source of the faint tremors we now detect on Earth with our gravitational wave observatories. Then, in a final, silent, catastrophic instant, the two event horizons touch. They merge, and in that moment a single larger and profoundly disturbed black hole is born. But the story does not end there. The new black hole is not a perfect placid sphere. It is the violent product of a chaotic merger. The two original black holes likely had different masses, different spin rates, and most importantly different spin orientations. Adding their angular momentum together is not a simple sum. It is a vector addition of unimaginable complexity, further complicated by the asymmetric blast of gravitational waves which can act like a rocket exhaust. This asymmetry imparts a tremendous kick to the newly formed black hole, sending it reeling away from the center of the merger at speeds of hundreds or even thousands of kilometers per second. More critically for our mystery, its final spin axis can be pointed in a completely new, almost random direction. It bears little or no relation to the spin axis of the larger of the two parent black holes. Imagine two spinning gyroscopes colliding at relativistic speeds. The resulting merged object would spin off in a new direction, its axis of rotation a chaotic compromise between the two originals. This is precisely what we believe happens in a binary black hole merger. The primary black holes spin the cosmic anchor that has dictated the direction of its jets for millions of years, is suddenly and violently scrambled. The galaxy's north pole is instantaneously redefined. Now picture the scene in the immediate aftermath. The cataclysm is over. A new, more massive black hole sits at the center of the galaxy, spinning on a completely new axis. But the vast accretion disk, the reservoir of fuel that survived the merger, is still orbiting in the old plane, the one dictated by the pre-merger dynamics. You have a situation of extreme, violent misalignment. The new black hole is spinning on, say, a horizontal axis, while the immense disk of gas is still orbiting on a vertical one. The central engine has been rebooted with entirely new operating parameters, but the fuel supply system has not yet received the memo. What happens next is the climax of this violent theory. The new black hole with its new spin axis begins to accrete material from the horribly misaligned disk. As this gas funnels in, it is forced to follow the contours of the newly oriented frame-dragging spacetime at the very center. The magnetic fields are anchored, twisted, and collimated according to the new rules, and a new set of jets is born. But these jets do not fire in the old direction. They erupt perpendicular to the new spin axis of the merged black hole. they blast out into the galaxy at an angle that could be as much as 90 degrees, or even more away from their predecessors. The old fading jets are still visible as ghostly relics, a memory of a previous cosmic order. But the new brilliant jets are carving a fresh path of destruction through the interstellar medium, a testament to the violent upheaval that has just transpired. In this scenario, the jet flip is not a slow procession. It is an instantaneous, brutal recalibration. It is the signature of a merger, the galactic equivalent of a scar from a near-fatal wound. It tells a story of two titans clashing, of gravity unleashed in its most furious form, and of a new monarch ascending to the throne, its reign announced by pillars of fire aimed in a new terrifying direction. So here we stand at a fork in the cosmic road. Two compelling narratives, each scientifically plausible, each leading to the same shocking outcome. One a story of slow, persistent grinding torque, the Lens-Thirring effect, Einstein's ghostly waltz reorienting a galaxy with the patient, inexorable force of a turning tide. It is a process of internal adjustment, a system settling into its lowest energy state over eons. The other a story of sudden, unimaginable violence, a binary black hole merger, a clash of gods that reshuffles the cosmic deck in an instant. It is a process of external shock, a revolutionary event that deposes the old order and installs a new one by force. Is the universe a place of gradual change or catastrophic revolution? Does it prefer the slow grind of space-time torsion or the brilliant flash of a gravitational cataclysm? The ghostly trails left by these flipping jets are clues, fingerprints left at the scene. But to truly know the culprit, to choose between the slow poison and the sudden blow, we need more than just a snapshot. We need to find the smoking gun. We need to catch the process in the act, a challenge that pushes our technology and our very ingenuity to the absolute limit. The verdict on this cosmic mystery is not yet written, and the next piece of evidence could be hiding anywhere, waiting for a telescope to peer into the dark and reveal the truth. We stand now on the shore of a new cosmic ocean, the familiar constellations of our knowledge rearranged. The journey we have taken together from that first flicker of anomalous data to the breathtaking confirmation of a universe in violent motion has left us fundamentally changed. The black hole, once a symbol of finality, of an unyielding and predictable end, has revealed itself to be something far more astonishing, a dynamic, temperamental, and perhaps even chaotic engine of creation. It is a profound and unsettling transformation in our perspective, akin to learning that the planet beneath your feet periodically and violently reorients its north and south poles. The bedrock of astrophysics has shifted, and every model we have built upon it must now be re-examined. This was never simply about witnessing a celestial marvel. It was about confronting the limits of our own imagination. We had envisioned the supermassive hearts of galaxies as gravitational gyroscopes spinning with an almost impossible fidelity for eons, their mighty jets locked into a single unwavering axis. They were the cosmic lighthouses, their beams fixed, carving steady paths through the interstellar medium for millions of years. This perceived stability was a cornerstone of our theories, a fixed point around which we could build our understanding of galactic life cycles. The discovery that these titans can wobble, that their poles can precess and flip on timescales that are cosmically instantaneous, is not an amendment to the old story. It is a completely new manuscript written in a language we are only just beginning to decipher. The shock that rippled through the scientific community was not born of error, but of the sheer audacity of the cosmos to defy our elegant, ordered assumptions. You have seen the faces of the researchers, a mixture of disbelief and exhilaration, as they wrestled with ghosts in their radiomaps and X-ray images. Each potential explanation, from instrumental glitches to gravitational lensing, was a desperate attempt to cling to the universe we thought we knew. But the evidence accumulated painstakingly by teams across the globe became an undeniable chorus, singing a song of unimaginable upheaval. The universe, it turns out, is a far messier, more unpredictable and infinitely more interesting place than our neat equations had ever allowed. What we have witnessed is the demolition of a paradigm, the humbling realization that our most cherished cosmic anchors can in fact come loose. And with this new dynamic reality, the implications begin to cascade outwards. touching every facet of cosmic evolution with the force of a shockwave. Consider the grand tapestry of a galaxy, a swirling metropolis of hundreds of billions of stars. For decades, we have tried to understand its architecture to explain why some galaxies are vibrant star-forming spirals, while others are placid red and dead ellipticals. At the heart of this puzzle was a concept known as galactic feedback, the process by which the central black hole regulates its own host. We imagined its jets as a focused celestial blowtorch, drilling a tunnel through the galaxy's gaseous halo, heating a narrow channel, and allowing the rest of the galaxy to cool and form stars unimpeded. It was a tidy, localized, and predictable mechanism. But now you must discard that image entirely. Picture instead a celestial fire hose gone wild, thrashing uncontrollably. This is the new reality of galactic feedback. A jet that can reorient itself doesn't just drill a single tunnel, it scours the entire galactic halo over millions of years. It becomes a chaotic, sweeping instrument of cosmic engineering. For 10 million years it might blast energy and radiation into the galaxy's northern pole, sterilizing vast regions, blowing apart delicate clouds of hydrogen, and preventing any new stars from taking root in that entire hemisphere. The gas is superheated, puffed up and rendered infertile for a cosmic generation. An entire galactic quadrant, which should have been a stellar nursery, is instead transformed into a barren, roiling wasteland. Then, in a span of just a few thousand years, the accretion disk wobbles, the black hole's spin axis precesses, and the jet pivots. Suddenly, that colossal beam of energy is aimed at a completely different, previously quiescent region of the galaxy. The southern pole, which had been peacefully cooling and condensing, is now subjected to a violent head-on assault. Meanwhile, the northern regions, no longer under attack, can finally begin the slow process of cooling down. The gas previously energized and dispersed can start to coalesce under its own gravity, setting the stage for a future burst of star formation where none was possible before. This isn't a gentle regulatory process. It's a violent, almost schizophrenic form of cosmic gardening where the gardener randomly alternates between pruning shears and a flamethrower. This single phenomenon forces us to rethink the very life story of a galaxy. A galaxy's evolution is no longer a steady linear progression. It is a history of violent fits and starts of dramatic reversals of fortune, all dictated by the chaotic whims of its central monster. The shape, size, and stellar population of a galaxy like our own Milky Way may not be the result of a calm cumulative history of mergers and accretion, but the fossilized record of its black hole's ancient violent tantrums. Where we see vast bubbles and voids in the interstellar medium, we might not be looking at the relics of ancient supernovae, but the scars left behind by a precessing jet that swept through that region 1 billion years ago. The distribution of stars, the location of stellar nurseries, the very morphology of the spiral arms could be a direct consequence of this relentless roving beam of destructive and creative energy. It transforms the black hole from a simple gravitational anchor into the galaxy's temperamental heart, its unpredictable metronome whose erratic beat dictates the rhythm of life and death on a galactic scale. And this grand sweeping impact on the galaxy as a whole drills down to the most fundamental process in the cosmos, the birth of stars. Imagine a vast, cold, dark nebula, a stellar nursery trillions of miles across. It is a delicate place, a cloud of gas and dust held in a fragile gravitational balance. For millions of years, it has been slowly contracting its core regions, beginning to clump together, forming the protostellar seeds that will one day ignite into a new generation of suns. In our old model, this cloud was safe unless it happened to lie directly in the jet's fixed path. But now we understand that no region is truly safe. The jet is a roving predator. One moment the nebula is at peace. The next, the leading edge of a particle beam moving at over 99% the speed of light slams into it. The delicate balance is shattered. The outer layers of the cloud are instantly ionized and blasted away into deep space, a process known as stripping. The nascent protostars are exposed to a torrent of lethal radiation, their developmental cocoons shredded before they have a chance to form. The entire nursery has aborted its potential for new life, extinguished in a cosmic instant. This is the destructive power of the flipping jet. It can enforce cosmic sterility, preventing stars from forming and fundamentally altering the galaxy's stellar census. Galaxies might be far less efficient at creating stars than we previously calculated, precisely because their central engines are actively sabotaging the process across vast rotating sectors. Yet this cosmic weapon has a paradoxical creative side. Consider a different kind of gas cloud, one that is more diffuse stable, and not quite massive enough to collapse under its own gravity. Left to its own devices, it might drift for eons without ever forming a single star. But as the sweeping jet passes by its powerful shock front, the bow wave of plasma and radiation pushing ahead of the beam itself compresses this lazy cloud. The gas is squeezed its density, soaring past the critical threshold for gravitational collapse. The shockwave triggers a cascade of fragmentation and condensation, igniting a furious burst of star formation in a region that was previously barren. The jet, the great destroyer, becomes the ultimate catalyst. It's a breathtaking duality. The same force that aborts one stellar nursery can simultaneously trigger the birth of another 100,000 light-years away. Our galaxy is not just a collection of stars. It is a dynamic battlefield of opposing forces, all orchestrated by the wobble of a singularity at its core. This duality extends to the very elements that make you me and our world possible. Stars are the forges of the cosmos, fusing hydrogen and helium into heavier elements like carbon, oxygen, and iron. When they die, particularly in supernova explosions, they release these precious materials back into the interstellar medium, enriching the gas for the next generation of stars and planets. But for this enrichment to be effective, these elements must be mixed distributed evenly throughout the galactic disk. A stable focused jet is a poor mixer. It punches a clean hole, leaving much of the galaxy's material unstirred and chemically primitive. But a processing, sweeping jet is a cosmic egg beater of unimaginable proportions. As it thrashes back and forth, its powerful winds and shock fronts churn the interstellar medium on a galactic scale. It dredges up heavy elements from the dense galactic center and flings them out towards the pristine gas clouds in the galactic suburbs. It takes the iron forged in one spiral arm and violently mixes it with the hydrogen clouds of another. This process dramatically accelerates the chemical enrichment of the entire galaxy. It ensures that the building blocks of planets and ultimately of life are not confined to isolated pockets, but are spread far and wide. The fact that our solar system, located in a relatively quiet spiral arm, is rich in heavy elements might be a direct consequence of this ancient chaotic mixing driven by the wobble of Sagittarius A millions of years before the Sun was even born. The very possibility of our existence may be tied to the instability we have just discovered. We may owe our chemical heritage not to a calm and orderly universe, but to a violent and unpredictable one. This cascade of revelations leaves us humbled but also electrified. Because for every profound answer this discovery has provided, it has opened up a dozen new, even more tantalizing questions. The central mystery, the one that will now consume the next generation of astronomers, is why. What is the mechanism that forces a supermassive black hole's jet to flip? What is the nature of this cosmic wobble? Is the black hole itself processing its spin axis, tracing a slow circle in the sky, like a dying top dragged around by the gravitational pull of a hidden companion black hole? The idea is staggering: two supermassive black holes locked in a final deadly dance, their combined warped space-time twisting the very direction of the energy output. If this is true, then systems like the one we've studied are cosmic laboratories for observing the effects of gravitational waves on a monumental scale, a prelude to the most powerful collisions in the entire universe. Or perhaps the culprit is not the black hole itself, but its accretion disk. Perhaps the disk is not the neat, orderly platter we see in simulations, but a lumpy, chaotic maelstrom of infalling gas clouds arriving from all directions. A massive cloud captured on a retrograde orbit could violently warp the inner disk, tilting it, and forcing the jets which are anchored to it to reorient themselves. In this scenario, the black hole remains stable, but its feeding apparatus is in constant turmoil. The galaxies, whether the random infall of gas and stars, would directly control the direction of its most powerful weapon. Distinguishing between these two possibilities, a wobbling black hole or a chaotic disk is now one of the highest priorities in all of astrophysics. It is the difference between understanding the fundamental physics of space-time and understanding the complex hydrodynamics of galactic ecosystems. To answer these questions, we cannot rely on the instruments of the past. We are staring into the abyss of a new cosmic mystery, and we will need new eyes to pierce the darkness. Humanity is at this very moment building those eyes. On the deserts of Chile and Australia, the thousands of dishes of the Square Kilometre Array are coming online, ready to map the radio sky with a sensitivity and resolution that will make today's observations look like crude charcoal sketches. It will not just find one system with flipping jets, it will find thousands, allowing us to perform a cosmic census to see if this behaviour is common, rare or universal. It will capture the faint ghostly radio lobes from flips that happened billions of years ago, creating a fossil record of galactic history written in magnetism and plasma. High above us, the successors to Hubble and James Webb are being designed on digital drawing boards. These future space telescopes will have mirrors of unprecedented size capable of peering directly into the chaotic light-swallowing regions just outside the event horizons of these distant monsters. They will watch in real time as clouds of gas are torn apart and funneled into the accretion disk, seeking the telltale signs of turbulence and tilt that could be the trigger for a flip. New X-ray observatories with the precision of celestial scalpels will trace the path of superheated gas as it is launched away from the black hole, mapping the magnetic fields that we believe give the jets their structure and power. And alongside these observational titans, a new generation of theorists will wield the power of supercomputers, creating simulations of such fidelity that they can model the dance of individual stars around a binary black hole or the intricate warping of a magnetic field in a turbulent disk. The path forward is clear. The great human endeavour of exploration, that innate drive to understand our place in the cosmos, continues. What began as a shocking anomaly on a computer screen has blossomed into a revolution in our understanding of the universe. We have learned that the cosmos is not a static museum piece to be admired from afar. It is a living, breathing, evolving entity filled with a violence and a creative energy that surpasses our wildest speculations. The black hole, the ultimate symbol of darkness and oblivion, has been recast as a dynamic sculptor of worlds, a chaotic engine of change. And we on our small, fragile planet are privileged to be the ones who get to watch, to wonder, and to slowly, piece by piece, pull back the veil on its deepest secrets. The story is not over. The greatest discoveries born from this one are still ahead of us, waiting in the silent, star-dusted dark.